Electricity, capacitance in circuits. Questions to ponder. What do capacitors do in circuits? How do capacitors combine in parallel? How do capacitors combine in series? And how do capacitors charge and discharge? Uses of capacitance. There are many uses of capacitors in circuits. Common use is in power supply circuits where we're converting from alternating current to direct current, and a capacitor is charged up to level out the bumps here when you convert from AC to DC. They're also used in tuning circuits with a device called an inductor, which is like a coil of wire, to slosh current back and forth and tune in particular frequencies. So when you're changing channels on the radio or TV, or even to tune in your cell phone, they're used in these tuning circuits. Also in timing circuits and timing devices, and even touchscreens, and many other uses for capacitors in circuits. We're going to just look at the very simplest configurations of capacitors in this video. We're going to start off by looking at capacitors in parallel, and we're going to do that because it's really the simplest simplest circuit configuration for capacitance. With a parallel circuit here, if we recall, the potential is the same everywhere within a conductor, and that's because it doesn't take any work to move the charge through a conductor here. So this positive potential is the same there as it is here, as it is here, and the negative potential here is the same down here as well. So the potential difference across these capacitors is equal, and also equal in this case to the source voltage. So since the voltage is the same across both capacitors, the total charge accumulated on both these capacitors is equal to the total capacitance times that voltage. So it's really this amount of charge plus this amount of charge, and that can be found if we add up both of these capacitors. So the equivalent or total capacitance in this circuit here with capacitors in parallel is simply found by adding up the two different capacitances here, 4 microfarads and 6 microfarads, and we get 10 microfarads. You can also visualize this as really just kind of increasing the surface area of the capacitors here when we put them in parallel. So by increasing that surface area, we increase the capacitance by kind of just adding those together. So this is our equation for capacitors in parallel, because the potential difference is the same on each. We're going to start off by looking at capacitors in parallel, and we're going to do that because it's really the simplest simplest circuit configuration for capacitance. With a parallel circuit here, if we recall, the potential is the same everywhere within a conductor, and that's because it doesn't take any work to move the charge through a conductor here. So this positive potential is the same there as it is here, as it is here, and the negative potential here is the same down here as well. So the potential difference across these capacitors is equal, and also equal in this case to the source voltage. So since the voltage is the same across both capacitors, the total charge accumulated on both these capacitors is equal to the total capacitance times that voltage. So it's really this amount of charge plus this amount of charge, and that can be found if we add up both of these capacitors. So the equivalent or total capacitance in this circuit here with capacitors in parallel is simply found by adding up the two different capacitances here, 4 microfarads and 6 microfarads, and we get 10 microfarads. You can also visualize this as really just kind of increasing the surface area of the capacitors here when we put them in parallel. So by increasing that surface area, we increase the capacitance by kind of just adding those together. So this is our equation for capacitors in parallel because the potential difference is the same on each. Capacitors in series. Capacitors in series, a little bit more difficult, not conceptually but mathematically here. The thing that we notice about capacitors in series is that when the negative charges run off of this capacitor over here, that leaves positives here for these negative charges to run to this plate. Well, where do they come from? They come from this plate of this capacitor, and they ran off of it, and therefore we can't place more excess negative charge on this plate than we have excess positive charge on this plate of this capacitor. So since that's true, the charge on each of these capacitors has to be the same. The charge is the same. Therefore, the potential differences will vary here. And what we'll find out is the potential differences will vary inversely to the capacitance here. So the larger the capacitance, the smaller the potential difference needed to place the same amount of charge as on this one. In other words, this had a smaller capacitance. Having a smaller capacitance, it takes a greater voltage to create give this or get the same amount of charge on this capacitor. So that being the case, what we see here is we can get the equivalent capacitance here, the total voltage, if you will. Remember, voltage or potential difference is Q over C. So the total voltage here is going to be equal to the sum of all of the voltages here. So this voltage drop V1 is equal to Q divided by C1, and this voltage drop V2 is equal to Q, the same charge, divided by C2. We don't have a third capacitor, but I just put this in here so that you could see that if we did have a third capacitor, we'd have to just keep stringing this out. Notice the Q's will cancel, and we get our equation here for equivalent capacitance. What you'd have to do is take the reciprocal and add them together of all of these, and then when you get the total there, you'd have to finally take the inverse of that. If we only have two capacitors in parallel, this is a simpler way to this is a simpler form of an equation to use. If you recall, it's like they're resistors in parallel. So capacitors in series, the equation is like resistors in parallel. And this is the simpler way to use it, the products over the sums, if you only have two capacitors. This does not work if you have three or more capacitors here. So using this simpler equation, since we have two capacitors, we can take the product of 4 times 8 microfarads and divide by the sum of 12 microfarads, and we get 2.67 microfarads. And just like resistors in parallel, when you're using this equation, your total or equivalent capacitance is always going to be less than your smallest value of capacitance here. So these are our two equations to use if we want to find out what the equivalent capacitance is in a series circuit with capacitors. And you can also see here that by putting these capacitors in series here, stacking them like this, the plate area might, kind of looks like it would be the same, but what we're playing with here is we're increasing the plate separation by putting them in series. That's another conceptual way you can see that the equivalent capacitance is going to be smaller than either of these two capacitors, because the plate separation is going to increase when we put them in series. So it's time for a sample problem, or problems. We want you to practice both a series combination and a parallel combination with a 60 nanofarad and an 80 nanofarad capacitor. So again, find the amount of equivalent capacitance in series and in parallel for these two capacitors. Come on back to the video after you've paused and given this a try. So how did he do here? Starting with the series capacitance here, and using since we only have two capacitors, we can use a simpler form of equivalent capacitance here, the products over the sums. And doing that, 60 times 80 divided by 60 plus 80, we would get 34. And since it's nanofarads, we'd carry the nanofarads down here. So 34 nanofarads is less than our smallest capacitor, so we feel pretty good about that solution. Next, capacitors in parallel are like resistors in series. They just add up, and that's super simple. 60 plus 80 is 140 nanofarads. The last circuit we're going to look at here is a circuit where we're going to be charging and discharging this capacitor. We're going to be charging it up to the 12 volts that we have as a supply here, and then discharging it back down to 0. So we're going to start here. We're going to flip the switch up and connect it to the battery. When it gets connected to the battery, this charging is not instantaneous. Because there's a little bit of resistance here, the current can't flow unimpeded, and so what we end up with is the capacitor will start to charge up to a voltage equivalent to this 12 volts, but it'll take a little bit of time here. So this is actually our equation that tells what the voltage across the capacitor is going to build up to over a certain amount of time, depending on the resistance and the capacitance here. And it's a natural logarithmic function here. And so as time goes by here, the capacitor will charge up more and more and more, and it'll increase at a decreasing rate, and that's what this shows, until it finally, where this will finally get close to 0, and our capacitor here will be the same voltage as our power supply voltage of 12 volts. And so it'll charge up until it's fully charged at 12 volts here. And as long as we have the switch connected up here, it'll stay fully charged. But then if we flip the switch down here, then the capacitor will no longer be connected to this supply, and we have connected it back onto itself here, and so the charge will actually run off of the capacitor and back around and discharge its opposite plate here. When it's discharging through this resistor, we get the same kind of a curve but in reverse or flipped over, and now we have a different resistor here. Before when we were charging, we had this resistance of 10 ohms. Now we have a resistance of 20 ohms here, and therefore it takes longer to move the charge off of this plate around to this side because it has to go through a higher resistance. And so this time is greater to discharge than it is to charge. And so this is an important feature of capacitors, is this idea of charging and discharging them. And in a lot of practical circuits, when you have capacitors in the circuit, they are connected to resistors after the circuit's turned off, like this kind of resistor, to discharge them on purpose so they don't sit around charged up. And those kind of resistors are called bleeder resistors to power down all the capacitors in a circuit. I encourage you to download the Capacitor Lab from PhET, and when you do that, you can put capacitors in parallel and see what happens if you do multiple capacitors here. And you can also put capacitors in series and play around with that as well, looking at what happens to the value when you change capacitance in series. So give that a go and see what it's have fun simulating. Again, you can search your browser, PhET Capacitor Lab, and enjoy that simulation. Questions to answer. What do capacitors do in circuits? How do capacitors combine in parallel? How do they combine in series? And how do they charge and discharge? And hopefully you're charging ahead on your quest for continuous improvement.